All right, so what we're going to be doing today is we're going to be looking at a bunch of different rules for derivatives. So what we're going to do is we're going to take that, that limit as h approaches 0 of the difference quotient, and we're going to apply it to a couple of different functions today to develop a couple of rules that we're going to use repeatedly so that we don't have to do that limit every time we want to find a derivative. So the first thing that we're going to do is we're going to look for the derivative of a function that's just a constant. So y equals 5 or y equals 100 or something like that. And so I'll tell you straight away that the derivative of a constant is always going to be 0. And hopefully that makes sense just based on what we know about what derivatives mean and what a constant function looks like. So what does a derivative mean according to the graph of something? It's just the slope of what?
The tangent line?
Right, it's just the slope of the tangent line to the function. And so if we're looking at a constant function, like for example here, y equals 3, then what is the slope of this function at every single point on the function, or the slope of the tangent line if we could draw one? It would always be 0. So the derivative of any constant function, doesn't matter if it's y equals 3 or y equals 4, or y equals 5 or -3, the slope's always going to be 0. So the derivative of any constant function should always be 0. Does that visually and graphically make sense?
Yes.
Yeah, okay. So let's algebraically show why that's true. So if our function is just a constant, so let's use the example of y equals 3. If our function is y equals 3, or in fact, let me change that. Let me make that
Would you like some more?
f of x equals 3. So our function is f of x equals 3. What is f of x plus h? If I replace all the x's in my function with x plus h's, what do I get? Are there any x's over here?
No.
No. So if I replace all the x's with x plus h's, does that do anything to my function?
No.
No, because there's no x's. So f of x plus h is just the constant. It's just 3, so constant. And what about f of x? Well, f of x is also just the constant. It's just, in this case, 3. So if we do f of x plus h minus f of x over h, we get the limit as h approaches 0 of just the constant minus the constant over h, or the limit as h approaches 0 of just 0 over h. And we still have a problem with this because if h is going towards 0, this becomes 0 over 0, so it's still indeterminate. But luckily, we know that we can simplify what's inside of here, and what is 0 divided by any variable. As long as that variable is not 0, what should we get?
0.
It should just come out to be 0, right? And h is never going to equal 0, is it? H is approaching 0, and our limit is only concerned about what happens as we get close to this value, not what happens at this value. So h is never actually 0, so 0 divided by h is always equal to 0. So we can simplify that there and say that the limit as h approaches 0, 0 is just the constant, right? The limit of a constant is the constant, so we end up with 0. So algebraically, that's the reasoning behind it. And graphically, we should be able to see it from what we know about the nature of a horizontal line. Good or no?
Yes.
All right. Cool. Now let's make it exponentially more complicated here. So our first rule is the derivative of a constant is 0. Our second rule is going to be the derivative of something like x to the power of n. And this is, a power, so we're going to call this the power rule. So if I wanted to write out the difference quotient for x to the n, it should look like x plus h to the n minus x to the n all over h. You guys agree with that? Everybody agreed that this is the limit as h approaches 0 of the difference quotient of that function?
Yes.
All right, cool. So you're going to have to take a little bit of a leap of faith with me here and assume that I'm correct and that this, all of that, without the minus x to the n, is the binomial theorem expansion of x plus h to the power of n. You get that from Pascal's triangle, right? The 1 is the coefficient here, then the n is whatever row you're in on Pascal's triangle, and then the next term can be derived by using n times n minus 1 over 2. The next one is n times n minus 1 times n minus 2 over 3 factorial, and so on. So this is just the expansion out of x plus h to the power of n. You don't need to know that, and you're not going to need to be able to prove this power rule, but just hopefully you can accept that this is that expansion. Everybody good with that?
Yeah.
Or no?
We're good.
Yeah? Okay. So whenever we expanded out one of these using this difference quotient, we always had everything that didn't have an h in it cancel out. True? So
Yes.
x to the n and minus x to the n, that still cancels out. So now we're just left with all these other terms that have these h's in them, and I'm going to write out a couple of them, but I'm not going to get too crazy with this. 2 factorial is just 2, right? So I can just write 2. All of this, oops, I missed my h on that one. All of this over h. Everybody good with that? We've canceled out the x to the n and the minus x to the n, but other than that, it should look exactly the same. Okay, so now all of those terms in the numerator have that h in them, and so we can divide all of those things by just the h, right? So what do we end up with? The first term just becomes what?
N times x to the n minus 1.
Yep. And the next term is going to become all of this same stuff just times h. And this next term will be all of this with just an h squared. And all of these h's will just drop down by 1 power. So I'm not going to write all of them out, but what does h to the n become if we drop that down by 1 power? H to the n divided by h should be what?
H to the n minus 1.
Exactly, right? Same basis. If we're dividing, we subtract the exponents. And so now, as h approaches infinity, h approaches 0, what is n times x to the n minus 1? Does that have any h's in it?
No.
No, so that should just stay the same, n x to the n minus 1. And what about this? Does this have an h in it?
Yes.
It's got an h at the end. So as h goes towards 0, I've got some number times some other exponent, or some of our x to some power times 0, which is going to become 0. And all of these other terms in this dot, dot, dot that I put here all have an h in them, which means they're all going towards 0. And this one is 0 to a power, which is also going to be 0. So everything except for the n times x to the n minus 1 cancels out. And that is the power rule. The derivative of x to the n always equals n times x to the n minus 1. Okay. So we take the exponent, bring it out in front as a coefficient, and then drop the power by 1. Does that make sense?
Yes.
Okay. This is a rule that you're going to want to know. Like I said, you don't need to be able to derive the rule. You don't need to prove that this is the derivative of x to the n. Okay? But you need to know that that's how you find that derivative. And you're going to know that really well by the end of the day today, because we're going to use it about 50 times today. Any questions on that process or the results? No? All right, so we're going to apply this rule to take a couple of derivatives, and you're going to start seeing some notations for the derivative. And I'm going to do my best to make sure I point out each one, but if I skip over one and you're not sure what something means, let me know. So first off, this is the power rule we just talked about. This d over dx means the derivative with respect to x. So all the with respect to x on the bottom part here means is that the variable within the equation we're looking at is an x. So the derivative with respect to x of x to the n equals n times x to the n minus 1. That's how this would be read out loud. And that's the notation for the derivative of something with respect to x. And like I said, with respect to x just means that the variable in here is x. So far good with the notation there and what that means?
Wait, so the whole thing just d over dx, that's just the notation for the derivative of the function x to the n power?
Yep, that's exactly right. This just means the derivative of whatever function I've got written over here.
Okay, got it.
Yep, that's what that means. And you're going to see that d dx notation over and over and over and over and over again. So the next derivative notation that we're going to look at is this one. This means find the derivative of f of x, f prime. So that little apostrophe is f prime of x. Okay, so if we're asked to find f prime of x, that just means find the derivative of f of x. So we can say that f prime of x should be equal to, and then we're going to take the derivative using the power rule of x to the 7th. So x to the n, or x to the 7th, that 7 should get brought down out in front. So we should get 7x to the 7 minus 1. And that's it. And that's a lot easier than writing out the limit as h approaches 0 of x plus h to the 7th minus x to the 7th over h, and expanding out that x plus h to the 7th and writing it all out and simplifying. And canceling, you just get this by using the rule that we've proven using the binomial theorem earlier. Does that make sense?
Yay! What clock I get to go back on?
Any questions on that?
So I have to do my math.
Okay. So this next one, y prime, this just means the derivative of y. So if we have y equals x to the 4th, what should y prime be? Y prime should be, using the power rule, what?
4 times x to the 3rd.
4 times x to the 3rd. That's it. Easy enough. Any questions on that?
What's up? You haven't even had any of your sandwich.
And what about this one?
Oh, no.
The derivative with respect to x of x to the 50th should equal what?
50x to the 49th power.
Yep.
Maybe you can have chocolate chips after dinner.
Anybody have any questions on any of those? Are those pretty straightforward, pretty easy?
Yes.
Okay, hopefully so.
How much more do you have now?
All right, so
How much more do you have?
the next thing we're going to do is we're going to put a constant in front of our function. So in this particular situation here, what we're looking at is u. We're calling u a function.
11 minutes?
We could call it u of x if we want, or we could have made it f of x. But u is our function, and we have a constant out in front of it. So if we want to take the derivative of a constant times a function, it just equals the constant times the derivative of u. Okay? And we could prove that by writing this out as a limit. And if the constant is in front of it in our entire limit, like I have a constant in front of every piece of it, can't we just pull that constant out for a limit? That's one of our rules for limits, right? And we end up with the constant times the derivative. Right. Does that make sense or no?
That makes sense.
That makes sense? Okay. And we should be able to apply most of the same rules that we did for limits into derivatives, because remember that derivatives now are just a limit that we're writing out in, you know, if we write it out in this limit notation, that's what a derivative is. Effectively, a derivative is just a limit. So all those same rules should apply.
6 plus 4 is 10.
So if I'm looking for the derivative with respect to x of 5 times x to the 4th, this is the same as 5 times the derivative with respect to x of x to the 4th. And what's the derivative of x to the 4th? Should be 4x cubed. And so if we multiply that by the 5, we get 20x to the 3rd.
Okay.
Any questions on that?
Or 2 circles. Okay.
From now on, you don't need to write all of these steps out in here.
Either 2 circles or
We'll
figure
note
8.
that we just take the power, multiply it by the coefficient, and then drop the power by 1, right? So this capital D with the subscript x, again, you could probably guess that means the derivative with respect to x of this function should be what if we use the power rule?
$88x to the 7th.
88x to the 7th, right? Multiply the 8 by the 11, gives you 88, drop down from x to the 8th to x to the 7th. Easy enough? Any questions so far on any of this?
I think I missed something. What does the du over dx mean?
Du over dx, this just means the derivative of the function u with respect to x. So if we have, you know, pretend like this was u equals, you know, 2x squared, du dx just means the derivative of u in terms of x, so 4x.
Or eat your sandwich, one or the other.
Does that make sense?
Okay, thank you.
Yep. All right, everybody good? Okay. Next rule we've got is a sum and difference rule. And so that one's just saying that if I have two functions, we'll call them u and v, that I'm adding or subtracting from one another, I can separate them and do the derivatives of each one separately, and then that's my result. Which should make sense again, because these derivatives, if you remember, are just limits, and with limits, I can separate one bigger function and do each limit separately if I want to. So I can do the same thing with derivatives, which means I can just apply the power rule if I, you know, if I have something like x to the 5th plus 3x cubed, and find the derivative of x to the 5th and the derivative of 3x cubed and add them together. So we should get 5x to the 4th plus 9x squared. Everybody good with that?
Yeah.
Okay, cool. So next one down here, if we're going to take the derivative dy dx of this function, we got 5 different pieces to it. We just take the derivative of each one and put them all together. So 4x to the 10th should give us what?
Uh, 40 times x to the 9th, right?
Yep, 40x to the 9th. What about plus 1/2 x to the 6th? That should become what?
3x to the 5th.
Okay. And what about 5x to the 5th should become what?
25x to the 4th.
25x to the 4th. And then what about minus 2x?
That's just -2.
Right, just -2. We have minus 2x to the first power. So that becomes minus 2x to the 0 power when we multiply by the 1 and drop it by 1 power or by 1 number. And x to the 0 is just 1. So that becomes minus 2. And what about the plus 3?
Do you need to take a break in order to?
2.
That should be 0 because, as we learned earlier, the derivative of a constant is 0. Everybody good there? All right. So everything we've done so far has just been with nice, simple integer values there, or even, I guess, whole number values, because we did some with powers of 0. But this power rule can be extended to use any numbers, not just the whole numbers, but it can be used for any value. So something like x to the -1, or x to the -4, or a fractional exponent like x to the 3/2, we should be able to still use the power rule for all of it. So if we're taking the derivative of x to the -1, this should become -1
Can't reach what?
x to what power?
Of what?
-2. And so this answer right here is a perfectly acceptable answer.
Okay.
Or we could rewrite it as -1 over x squared, which is also a perfectly acceptable answer.
You can do it.
I don't have any preference between the two, but sometimes it's going to be necessary to rewrite it into this form so that we can do some other work with it. Does that make sense? Everybody good with that one?
If you need to stand up to it, that's fine.
All right, what about the next one? What should this one become?
Say that instead of whining at me.
Oh, there's a question in the chat.
Oh, is there? I must have missed that. Sorry. Yeah, -x to the -2. That's fine, Dylan. Yeah. That's no problem at all. Anytime it's got a coefficient of 1, you don't need to write it. All right, what about this next one? What should this become?
-4x to the -5th.
Okay. And we could write that if we wanted to as -4 over x to the 5th. Yeah? Everybody good there? All right, what about this next one? X to the 3/2. If we want its derivative, that should become what?
3/2 times the square root of x.
Right, 3/2, and it's x to the 1/2. So we could rewrite that as 3/2 the square root of x, right? 3 root x over 2. And either one of those, again, is just fine. All right, and so for this one, square root of x, we could write this as we're looking for the derivative of x to the 1/2 power. And what's the derivative of x to the 1/2 power using that rule? It should be 1/2 x to the -1/2. Or we could write this one as 1 over 2 root x. And this is another one you're going to want to have memorized. Is that the derivative of square root of x is 1 over 2 root x. Comes up very often, so it's just going to be convenient if you don't have to write it out and figure it out every time. So far, good? Everybody all right so far? Okay. You guys want to try and do these two on your own, and then we'll talk about them real quick? I'll take that as a yes. Do these two. I'll give you a couple of minutes, 2-3 minutes to do these. Shouldn't take very long, and then we'll go over and make sure you get them right. What did you guys get for the first one? X to the 2/3 should become what?
Two-thirds times x to the negative 1/3.
Yep, exactly. 2/3 x to the negative 1/3, and then the 4x to the negative 3 should become minus 12x to the negative 4. This is perfectly fine. If you wanted to write it as 2/3 cube roots of x minus 12/x to the 4th, that would be perfectly fine also. Or if you want to just change one of them, that's fine too. Everybody good with that? All right, what about this one? First term should become x to the negative 4/5. Next term should have been plus 10x to the negative 6. And then the last term should have been plus 6x cubed. Is that what you all got?
Yes.
Any questions on either of those? All right, make it a little bit more complicated. So we got a bunch of weird looking roots in here. I just want to make sure you guys are able to convert each of those roots into a fractional power so that you guys can take the derivative. So if we're looking for the derivative with respect to x of this, that's the same as the derivative with respect to x of root x we know to be x to the 1/2, right? And then this is the 4th root of x cubed, so that should be 5x to what power? Before we take the derivative, it's the 3/4 power, right? Yeah, good. The power divided by the root, and then minus x to the 1/10. So when you take the derivative of that, you should get, we know this one already as 1/2 root x, or 1/2 x to the negative 1/2. And then we need to multiply that one out to get plus 15/4 x to the negative 1/4. And then minus 1/10 x to the negative 9/10. Any questions on that? Everybody good with that? Okay, what about this one? This 1/root x is x to the negative 1/2, right? And so when we take the derivative of that, it should give us negative 1/2 x to the negative 3/2 plus 15x squared. Everybody good with that?
Yep.
All right. So hold on one second. These are higher derivative powers, but hold on one second. I'll be back in a minute. Okay, sorry about that. So what we've got here is all the different notations that we've already talked about. So like f prime of x is the first derivative, y prime is the first derivative, dy dx is the first derivative. This capital D subscript x of y, of whatever we're plugging in there, is the first derivative. So we also have what's called higher order derivatives, or second derivatives, or third derivatives, or fourth derivatives, or nth derivatives. So the two little apostrophes is just read as double prime, or the second derivative of f. So this is f double prime, or the second derivative of f. This is f triple prime, or the third derivative. This we just call the fourth derivative of f. And same here, y prime, y double prime, y triple prime,
Why? I'm not
the
doing
fourth
homework.
derivative
Eat
of
your
y.
ass. Why?
1 second. And then again here, dy dx, second derivative of y with respect to x, third derivative of y with respect to x, and so on. Same with these ones. Everybody good with that notation? You're going to start seeing these. We're going to be finding these higher order derivatives right now.
Still eating your sandwich?
Any questions on those
Put it in the
notations?
box so you can have it for lunch tomorrow.
Problem solved. I don't want to put it in Tupperware or can get smaller.
All right, so let's see if we can find the first four derivatives of 2x to the fifth. Should be pretty straightforward. The first derivative is what?
10x to the fourth.
10x to the fourth, exactly. So our second derivative is just the derivative of our first derivative. So what's the second derivative of f? It should be what?
40x cubed.
And our third derivative should be 120x squared, and our fourth derivative should just be 240x.
Don't bother your brother.
Any questions on that? Everybody good with that?
Are you coming with me? No, you have homework to do.
I didn't have any more.
Well, then you're coming with me to Boston.
Why? I want to go.
All right, you guys do these first four, and we'll check them in just a second. So see if you can figure out those first four on your own. All right, sorry about that. Everybody got your first four derivatives there? What's the first derivative come out to be?
Two times the square root of x.
I don't think it's 2. It should be 6, right? 4 times 3 halves should be 12 halves. So 6x to the 1/2, or 6 square roots of x. Everybody good on that being a 6 out there? 6x to the 1/2?
Mm-hmm.
Yeah, I forgot division for a minute.
Ah, yeah, that's no good. You need to remember that. All right, so f double prime should be what? Just half of 6, or 3x to the negative 1/2. And the third derivative then should be what? Negative 3 halves x to the negative 3 halves. And our fourth derivative should be what?
9/4 x
9/4,
to
yeah.
the negative 5 halves.
Yep, everybody good with those? Everybody feel like they could do that?
Oh, wait, question.
Yeah.
When there's too many primes, can you just put a number next to the f like that?
Sorry, say that again?
When there's too many primes after taking a bunch of derivatives, can you just put like a number in the top like that?
Sorry, say that again. I'm not understanding what you're saying. If there's a number in front of it, oh, you mean just like negative 3x to the negative 3 halves all
Oh,
over
no,
2?
like, you know how you notate f, like derivatives of an f prime?
Oh, yeah.
Can you write a number in the top like that if there's too many like apostrophes?
Yeah, so for f prime, f double prime, and f triple prime, you write the apostrophes, but after that you just do the number, whatever, you know, fourth derivative, seventh derivative, and so on. Yeah. Does that make sense?
Yes, thank you.
Okay, cool. Yeah, sorry, I didn't understand what you were saying. I got some attitude going on in the background from my 12-year-old. So, yeah. All right, let's find the first four derivatives of this. F prime of x equals what? Negative 6x to the negative third, right?
Yes.
Okay, and what about the second derivative? 18x to the negative 4. And our third one should become what?
Negative 72x to the negative 5.
Good, and the last one should be what? 360x to the negative 6. Everybody good with that?
Makes sense.
All right, you guys do these four for this one. This is the last one we'll do the first four derivatives of. And then we'll move on to some other stuff, and then we'll be done pretty. These ones should be pretty easy, I think. F prime should be what?
100x.
100x. F double prime should be
Just 100.
just 100. F triple prime should be
0.
0, because the derivative of a constant is 0. And our fourth derivative should be also 0, because the derivative of a constant is still 0, right? And the fifth derivative and the sixth, and all the way up to as far as we want to go, the 100th derivative of this should all just be 0. Everybody good there? All right, so we're going to do 2 more problems here, and we're going to just take a look at a real basic application of what these derivatives can sort of do for us, and we're looking at the graphs of functions. So what we're going to try and figure out is if the curve y equals x to the 4th minus 2x squared plus 1 has any horizontal tangent lines. And so when we talk about a tangent line's slope, that's our derivative. And if the tangent line is horizontal, then what does that tell you about the slope of the tangent line? Should be equal to what? It should be 0, right? Because a horizontal line has a slope of 0. And if the slope of the tangent line needs to equal 0, then that means that the derivative dy dx needs to equal 0. Does that make sense? Any questions on that? Everybody good with that? Okay, so let's find the derivative of this, and then we're going to set it equal to 0. So see if you can get the derivative and set it equal to 0 and solve for x. So dy dx should have come out to be what? 4x cubed minus 4x. Is that what you all got for your derivative?
Yes.
And we set it equal to 0. And how do we solve that equation? We should do what with it?
Factor it.
Yep, just factor out the 4x. So we have 4x times x squared minus 1 equals 0. And then using the 0 product property, we can set each piece of it equal to 0. And that gives us x equals 0 and x equals plus or minus 1. So what we need to do now is we need to take a look at the graph. 1 second, I'll pull the graph. Okay, sorry, you guys can see the graph up there now, I hope. X to the 4th minus 2x squared plus 1.
Yes.
Okay. Yeah, sorry about that. We're having some issues with my 7th grader. He doesn't want to, do anything with his life. So we've got x equals -1 and x equals 1 were 2 of our solutions. And if we were to try to draw the tangent line there, we'd see that it should be horizontal, right? A tangent line to this graph is horizontal both at x equals 1 and -1. And also at x equals 0, which was our other solution, a tangent line to that graph there should be horizontal, have a slope of 0. And we should note about the graph that it's got a little local minimum here and a local maximum, and then another local minimum at each of those points. Everybody see that?
Yep.
Okay, cool. So if we wanted to, we could take each of these values, x equals 0 and x equals plus or minus 1, which this is our answer because it asks where do they occur. But we could plug those in up here. And if we plug in x equals 0, what do you get for y? You'd get y equals 1, right? And if you plug in +1 to this or -1, you should get y equals 0. And so if we go back to the graph and look at y equals 1, that's that horizontal line tangent to the graph at this point. even though it does cross through it at other points, at this particular point, it's tangent to the graph. And then down here, y equals 0. Same thing, it's tangent to the graph at those points, negative 1, 0, and 1, 0. Everybody good? Any questions on that? All right, one more. I want you guys to see if you can get through this one all the way on your own, and then we'll go through it and see how it worked out for you. It shouldn't take too long, and then we'll take a look at the graph. I'll give you just a minute or two to look at this one. All right, so what did you get for your derivative?
X squared minus 4.
Good. And we should set it equal to 0 because we're looking for horizontal tangent lines. And we're going to do that a ton more times this year. We're going to set things equal to 0 for horizontal tangent lines and solve. And solving that gives you x equals what? Plus or minus 2. And so if we go in and we take a look at the graph, of what is it? 1/3 x cubed minus 4x plus, what was it? Plus 9, I think. If we look at the graph there, we can see that at 2, we have that local minimum, and that's where we'd have a horizontal tangent line at x equals 2. And the same at x equals negative 2. We've got that horizontal tangent line for that local maximum. Right? And if we wanted to, we could go in and we could figure out what those values actually were for those tangent lines. We could do that. So if we plug in 2, what do we get? We get y equals 1/3 of 2 cubed minus 8 plus 9. And if we plug in negative 2, we'd get y equals 1/3 times negative 2 cubed plus 8 plus 9. And so this one is, what is that? 8/3 minus 8 plus 9. So 8/3 plus 1, which is 11/3. And this one we'd have negative 8/3 plus 17, which is 51/3. So what does that come out to be? 43/3, I think. I did that right. Hopefully I did that right in my head. And let's take a look at the graphs of those. What did I have? I had 11/3, right? And what was the other one? 43/3. Oops, 43/4. 43/3. There we go. And so tangent to it right there, tangent to it right there. We've got our 2 horizontal tangent lines. Everybody see that?
Yes.
Everybody good? Any questions on any of what we've done today? All right, that should be it then for today. I think we're done a little bit early again.